Hello everyone, welcome to this video. My name is Amir Senahri. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how we can get elevation value for the water bodies or inland lakes in the Google Earth Engine platform using JavaScript. So let's go to the Earth Engine code editor environment. So first of all, we need to identify the region of the interest using drawing tools available here. You can use this code and use this tutorial for all around the world, and also it doesn't matter which location or which the lake or which the region you are selecting in this study, because the data I'm using, all of them available publicly and globally. So now I want to select a lake in my own country. My country is Iran, and in the northwest of Iran there is a big saline lake, and this is the Urmia lake. Using drawing rectangle here, I want to select these lakes, as you can see. So for the next step, I want to show you how we can get the average elevation of the water body for this lake, one for 2000 or 2001, depends on the availability of satellite data. And the next, I want to check the lake elevation in 2023, and I want to compare them and show you how we can get these values for the lake area variations. This is a very helpful technique in the remote sensing applications in hydrological studies. So next, we need to identify, we need to have focus on the study area through the map.center object. Map.center object inside geometry. Inside parentheses, import geometry. Here, when you run the code, as you can see, we will have focus on the study area that is selected by drawing tools. Next, we need to call satellite data to get the water bodies through the search places and dataset. Before that, make a new variable. I want to use MODIS satellite images available for between 2001 and 2024, and also still MODIS data publishing near real time on different websites, including Google Earth Engine and Earth Data, and you can download and use it. So through the search places and dataset, write MODIS surface reflectance products. MODIS surface reflectance product. As you can see, a variety of MODIS surface reflectance products are available. Some of them for Terra and some of them for Aqua. Aqua and Terra referring to the satellites that carrying the MODIS sensor. Actually, the Terra and Aqua, the main difference between these two satellites is the starting date. Terra is available since 2001, I think, or 2000, and Aqua is available since 2002 or 3. I'm not sure. Yes, it's from mid 2002 available. So, and the next difference is between the temporal frequency. Originally, MODIS data available with daily temporal resolution, but as you know, the daily satellite images always including more cloud cover and more noises, and also but in multi-temporal collections such as 8 days or 16 days products, less cloud cover and also less noises existed. And now I prefer to use 8 days data because I don't need to the daily frequency. Just I want to extract the water body for the whole of, for example, 2001 or 2002 and get an average, and I don't need to monitor the variation of the lake during days, weeks, or months. Just one average image is important for me, and I prefer to work with the data with less noises and less cloud cover in this application. Depending on your application, you can choose any other type of satellites data with different temporal frequency. So And the next is the spatial resolution. Some of the products available with 250 meter spatial resolution, only including band number 1 and 2 in the red and near infrared region of electromagnetic spectrum, and some of them available with 500 meter spatial resolution, including band number 3 to number 7, that are multispectral bands in the visible and near infrared and mid infrared region of electromagnetic spectrum. And also, if you want to have more accurate border for the lake area, I recommend to use 250 meter spatial resolution. But the main limitation in this product is that we don't have access to the green band, and only we have to calculate the NDWI through the relationship between red and near infrared region of electromagnetic spectrum. And also, in my experience, there is no clear or concrete differences between NDWI using red or green bands, at least in the applications I tried. But it depends more research and more study to judge about that. But here, spatial resolution is more important for me, and I prefer to use 250 meter spatial resolution data. So accordingly, choose a Terra surface reflectance product with 8 days temporal frequency that is global with 250 meter spatial resolution, imported into the code as an image collection. And next, make a new variable, for example, modis 2001 equals to image collection. And then in the next step, I want to select the temporal period that I want to call modis data for. And using that filter date, we can set a start and end date to narrow down modis images or modis collections to a specific period of time or time span we want to study. For example, I want to get an average value, I want to make an average image for NDWI in 2001. So starting date is 2001 and ending date is 2002. And as MODIS data provided coarse spatial resolution, they don't have framing structure such as Landsat and Sentinel, and you don't need to set filter bound in your code when working with the MODIS products. At least for the MODIS surface reflectance product, you don't need to set filter bound anymore in the Google Earth Engine platform. When we want to get a result through some of the arguments, we can get our results specifically for the border that I drawed here, or the rectangle that identified our study area. So for the next step, I need to calculate the NDWI for all images that are available under MODIS 2001. To do this, make a loop through the map, and inside the parentheses, make a function, and in the function, each input image should be considered as an IMG or any other name you prefer. And then in the body part of function, we can write the desired equation. Don't forget to check the data description regarding to the scale factors or any pre-processing that should be considered in this regard. For example, and also should be noted that MODIS products, all of them corrected, or all the satellites data available in the Earth Engine, at least most of them, all of them pre-processed completely, and they don't need radiometric and geometric correction. But for some of them, we need to apply a scale factor to ranges the band values from the integer range to the right and precise float range. So for example, most of the time for modest data there is a scale factor that should be considered in the calculation, meaning that before further processing, before calculating any indices, first you need to convert a reflectance band 1 and 2 by the scale factor into a correct range of value for reflectance, and then calculate the NDWI based on. So now I want to select all the bands starting with SUR. Back to the code, and as you can see the band names. Before that, through .select, you can select the desired band starting with SUR, and the rest of them is not important. So now make a variable in the body of your function and get each input bands and then multiply them, because we have two bands here, to the scale factor that is like this. And then for the next step, the NDWI equation equals to make a variable NDWI normalized difference water index, or NDWI, equals to get the band first and then through the normalized difference you can get the normalized relationship between the red and near infrared bands. So here I want to use a normalization relation to get the normalization relationship between band number 1, or red region of electromagnetic spectrum, and the near infrared with 250 meter spatial resolution. Although the main NDWI index uses green wavelengths instead of the red, but here, as I needed higher spatial resolution, I preferred to use band number 1 and band number 2 to have access to 250 meter spatial resolution instead of 500 meter. So, and finally, through that rename, set a name for the bands that is calculating, that is NDWI, and finally the function returning NDWI, just like that. And then for the NDWI, for each NDWI, we can integrate all of them together or aggregate all NDWIs for each pixel to the average value. But here, to get an average, would be better to use median instead of the mean or average, because median including less cloud cover at the end and less shadows and provided more realistic results compared to the average, because most of the time the average or mean affected from the high extreme values or low extreme values, and such extreme values coming from cloud and noises, but median less affected. So, and now I want to show you the median image for NDWI that is calculated for 2001. Map.add layer, inside the box or inside the parentheses, I want to show MODIS 2001 and then clipped based on the region of the interest, and leave the visualization parameters empty and set a name for the layer setting that is 2001 or NDWI 2001. And to avoid automatic visualization or automatic loading of final image, set here false. Run the code, and after a few seconds, through the layers, NDWI for 2001 is available. So now you can see the NDWI image, the average of NDWI for this year. As you can see, the NDWI highlighted water area or the water surface in our study, in the region of the study, in the region of interest or the case study. And now I want to get area of water body for this year, because I want to get its elevation, the average valley elevation over the water body or over the lakes available here. So to get the shapefile or to get the border of the lake here, we need to set a threshold to actually to separate the water body from non-water pixels. Through the inspector, you can see the range of values that we have in the water body and non-water body. For example, in the water, you can see NDWI is 0.7, values greater than 0, and also non-water pixels, including the negative values. If you want to see the range of values more accurately or precisely, you can use the histogram technique. Using the print and charts, you can draw the histogram for this image. Histogram for image for MODIS 2001 that is clipped. Or no need to set a clip here, because instead of clip, we can set the geometry, and we want to get the MODIS NDWI histogram for the region of the interest and according to the spatial resolution, because the spatial resolution identifies the number of pixels available in the region that I have selected as geometry. So let me to make the right panel bigger in the console. After code is run, you can see the histogram for this region. This is the histogram of NDWI for the region. As it is expected, we have a multimodal histogram here, and the first mode or the first peak showing the located in the negative values that is related to non-water pixels, and the second peak related to the positive values starting from 0 that's showing the water pixels, because in the NDWI image, water pixels highlighting with a brighter color and with a white color and with including higher values. So now we can say that the values greater than, for example, 0.1 can be a good threshold to separate water from non-water pixels. So to do this, make a new variable, threshold equals to 0.1, and I want to select from MODIS 2001 those of pixels greater than those of pixels that their values are greater than 0.1. Next, through the map.add layer, you can see the binary image that is created after this. I want to show the threshold here that is clipped for the region of, according to the border of region of interest, and leave the visualization parameter empty and write the layer name as lake threshold, and then use the false at the end. After a few moments, you can see the binary image that's showing value number 1 for water and value number 0 for the non-water pixels. As I want to make a shapefile for the pixels value number 1, we need to mask or remove values pixels with values number 0. So to do this, we can use the update mask. So seems I have a problem here. Now it is solved. So make a new variable. We want to make a mask for the data provided for 2001 equals to get the binary image thr, and then through the update mask you can remove the extra pixels that's showing dark region. Then through the map.add layer, you can see the differences between mask and threshold images. Here we want to show mask 2001 that is clipped based on the geometry, and then without parameter for the visualization, and the name is mask 2001, and finally we will have false. Run the code and turn the background to the satellite to have a better contrast between foreground and background. And now you can see the zero values all removed, and only we have the lake body. So, and now we can convert the lake body for 2001 to a vector layer. It's very simple part. Make a new variable, vector layer for 2001 equals to get mask from 2001, and then throw the reduce to vector, reduce to vector. Now we can convert this grid structure we can convert it from grid structure to the vector structure. So the reducer, it's not important here. The only arguments matters here is the geometry equals to the geometry, the region of the interest, and the scale is also important, should be equals to 250. So now through the map.add layer, I can show you the vector layer for the water body in 2001. It's very simple technique, and also you can use this shapefile for the further analysis in the GIS based desktop softwares such as ArcGIS Pro and so on. So through the map.add layer, as you can see, map.add layer, I want to show vector 2001, and that is clicked based on the region of the interest, that is geometry, and also it's not mandatory to, it's not very essential to clip the vector layer based on the region, because we already defined the geometry as a region of the interest before. So leave the visualization parameter empty, and here we have a lake for 2001, and then use the false, and finally here you can see the lake for 2001 is created, and we are waiting to show the final result. As you can see, this is the vector layer for the lake area, for the lake body in the 2001 that is created very well. And now I want you to use this shapefile for the next part to get the average elevation value over this region, and also this could be my region of the interest for the next part. So, and but the question is how we can get the average elevation over the lake body in 2001. To answer this question, the first thing we need is the digital elevation model that is globally available. Most of the remote sensing users prefer to use SRTM digital elevation model. That truly is one of the best products for the digital elevation model. But there is one limitation in this product. The SRTM only available for mid-latitude region. If you are living or working in the high latitude regions, for example above 60 degree, and you, for example in Scandinavian countries or Canada in some parts, you can't have access to the SRTM. We have a lack of SRTM frames for the high latitude regions. That's why I prefer to use ALOS Pulsar, ALOS Digital Elevation Model. As you can see, DEM, ALOS DEM. You can see that ALOS DSM, Digital Surface Model, is also available with 30-meter spatial resolution. The main advantage of ALOS DSM compared to the SRTM is the global coverage actually. And now I want to import it into my code as image collection number 2. and as also it has framing structure, you can have access to the ALOS data as image collection for the region of the interest. So, and now make a new variable to get a digital elevation model for your region. And DEM equals to get image collection number 2, and then throw the mean. I want to integrate all the DEM scenes together into a single file, and I want to avoid from framing structure by this. I want to mosaic them by the averaging method here. And the next, you must select the desired band that's showing elevation value in this product. Go to the data description and bands. You can see that we have DSM, digital surface model, height above the sea level in meter. It is available, so that's the target bands available. Now I want to copy and paste it into the code to select the target band, and here I have my target band. And in the next step, I can use this digital elevation model to get the average value over the lake area, or over the lake border. So now to visualize the digital elevation model, I can use map.add-layer, as I have already showed you how it works, and now you are an expert to visualize in the Earth Engine platform, because lots of times I'm using map.add-layer to visualize the results for each part. Map.add-layer, inside the parentheses, we want to show the digital elevation model. That is no need to clip. You can also compare different regions by this, and leave the visualization empty, and the layer name could be digital elevation model, and use the false at the end. Here, when I check it on, you can see the elevation values for all around the world. By increasing the contrast, you can see a grayscale image from a brighter region to a darker region. In the DEM, or digital elevation model, is a kind of raster layer that is here from ALOS, created from the radar images that showing the topography of the Earth's surface, and it has a grid structure, and each pixel showing the elevation for that. For example, this pixel elevation is 2,325 meter above sea level, and for example here we have a peak for the in the mountainous region, and the elevation value is above 2,000, near to 3,000 meter above sea level. And also in the lake region, that is here, we have lower elevation values, around 1,000 meter above sea level. So now I want to get the average elevation over the lake body that is extracted from the satellite data for 2001. And now I want to make a new variable as lake elevation for 2001 equals to get DEM, because I want to get the elevation. So I need elevation data, and the elevation data is digital elevation model, or DEM. Get DEM first, and then through that reduced region we can get the elevation value for this area. That reduced region, one of the important arguments is reducer, Earth Engine dot reducer. If you want to get the average elevation, reducer dot mean. And then for the geometry is important. The geometry should be the area that is covered the lake, or the shapefile that we created for the lake, that is vector 2001. The main difference between vector 2001 and primary and also the first geometry is that the first geometry showing a lake and non-water pixels in our region, but Vector 2001 or Lake 2001 only consistent with the pixels that including water and covering the lake bed. So, and next important is scale. A scale should be equals to 250 because the spatial resolution is this. And to get the final value, use that values and that get item number, get it's the first item, that is get 0. And to convert it from dictionary structure to a number, use Earth Engine number to convert the final value as a number. Now I want to print the final results. Here we have lake elevation for 2001 equals to, here we have lake elevation value, and then run the code. In the right panel you can see the elevation average over the lake, that is 1268 meter. So that's very simple and also easy to use method. Instead of mean, you can get different options or items regarding to the lake. For example, we can get the maximum elevation point, we can get the minimum elevation value, or median, for example. It depends on you which kind of information you want to get regarding to the lake condition. So, and also you can calculate percentile. For example, dot percentile. Using dot percentile, I want to, for example, percentile 55 or percentile 50 usually correspond to the median value. Also, there is no such difference. And also, if you want to get the maximum but not included, for example, some extreme pixels, you can get a percentile 75 that give a sense or give an insight about the maximum value over the lake without considering some extreme points. So, and also you can use a variety of statistical parameters here to get relevant information in your work. So, for example, I use 55 that is equals to median value or median of elevation in this region. So this is the average elevation value that we get for a lake in 2001. And now if you want to, for example, if you want to download the shapefile layer, for example, Vector 2001, it's very simple things. Just use export.table to drive. Here we want to get an export from a shapefile, and instead of export.image, I'm using export.table to drive. The collection or the shapefile you want to save is Vector 2001, for example, and the description, the name of the output, the description should be, for example, Lake 2001, and folder, I want to make a folder with a name, for example, lake border, to save the output in a specific folder as lake border in my Google Drive. So, and the file format is very important here. The file format equals to SHP, that is showing the shapefile structure for the vector layer, that helping you to open it up in all the spatial analysis softwares. So now you can save your code and run it. And after a few moments in the task, you have a lake 2001, a vector layer. Click on run, again run. And also we need to wait until the process of saving into the Google Drive is ended, and after the panel color turn to the blue, just like previous one, we can download the vector layer with different systematic files and use it into QGIS to see how the final result will be shown in the in the desktop softwares. So now you can see that it's over, it's very fast, and click on opening drive. You can see we have a new folder as lake border, and also the shapefile layer created with systematic files dbf, prj, shp, all of them are available. Select them all, right click, and go to the download. Google is zipping all files into a zip format, into a single file, and after it is downloaded we can open it into the, for example, QGIS software. Go to the QGIS, ArcGIS, or any other spatial data analysis software that you are using, no matter which software you are working or you need or you have. In the QGIS, through open data source, we can open it, and also in the left panel select the vector and vector datasets. You can browse it through here. So the output will be in the downloads part, but unfortunately I need to go to the folder and zip it. Oh yes, it is unzipped already, but if you have it in the zip format, you need to extract it and bring it out from the zip structure. So I go to the download part, and also this is the final result. Only select the SHP format and add it into the software. As you can see, the shapefile is ready to use, and you can do any spatial analysis in the QGIS. It is a kind of data mining approach we are using in the remote sensing through the satellite images. Through the machine learning techniques, we're able to produce such kind of information for the modeling and further studies in the next steps. So back to the code, and now I want to repeat all these codes for 2023. No need to write a new code, just with a little copy and paste I can use it for 2024. For example, you can see that MODIS 2001, I select this here, copy and paste it, and this time I want to use that for 2023. Same image collection, same bands. The only thing changed is the year. Starting years should be equals to 2023, and the ending 2024, and also everything should be same. And for the next part, just no need to visualization anymore, and threshold is same, and also the mask should be changed here. For example, oh yes, threshold should be changed because the input of threshold is MODIS 2001, and now I need to change it to 2020, 23 actually. So the threshold number 2 equals to get MODIS 2023 values greater than 0.1, and then we need to mask them all. Just a simple copy and paste for 2023, get threshold number 2 and update mask based on the threshold number 2. Back to the code and use the vector variable, copy and paste it again with a little change, but now we have vector 2023 that getting from 2023 the layer, the lake layer. And now for the visualization, now we can compare the lake in 2001 and 2023 to see that how much the lake area changes visually. The vector 2023, lake 2023 again, and run the code. And finally, you can see the lake border here. It takes a little time to visualize the final results. Yes, you can see that how much the lake border decreased over these years because of desiccation. And this is lake 2001, and after 2001 you can see that after 20 years or more, you can see that how much the lake area decreased here because of desiccation. And also, and then we want to get the average elevation for this region. It's very simple, the same digital elevation model, no need to change anything, just we need to copy and paste lake elevation from 2001 to 2023. From 2001 to 2023, get the DEM value, and also the only thing changes is vector 2001. Instead of vector 2020, 2001, we will have vector 2023 with the same spatial resolution and percentile 55%. And through the print, you can show that how much elevation is in 2023. That's it, the elevation for 2023, just like that. It's very simple, and also the same code for 2 different years. You can see that how much the lake elevation decreased after changes occurred in the lake. So you can use this tutorial for all around the world, and I hope you like this tutorial because I have tried a lot to make it as simple as I can to be helpful for you in your own projects. If you had any problem regarding to the programming steps, you can find the codes link below the video in the description in my YouTube page. And also, if you had any problem in this regard, you can put the comments in my YouTube page. I will check and answer you as soon as possible. Thank you for the attention.